Buenos días a todos. Bienvenidos a los seminarios del Instituto de Biología de la UNAM. Para los que nos están siguiendo por primera vez, tenemos esos seminarios todos los martes a las 11 de la mañana durante el tiempo que dure la cuarentena. Entonces, el próximo martes vamos a tener el seminario del doctor Alejandro Tomescu de la Universidad de Humboldt State en Northern California, que nos va a hablar sobre The Still Concept, a Never-Dever Perspective. Y entonces hoy tengo el gran placer de estar con el doctor Daniel Brooks, que es profesor emeritus de la Universidad de Toronto y Senior Research Fellow de la Universidad del Museo de la Universidad de Nebraska. Él nos va a hablar, entre otras cosas, de un libro que ha publicado que se llama The Stockholm Paradigm, Climate Change and Emerging Diseases, que publicó en University of Chicago Press. Es un biólogo de la evolución que ha hecho muchísimos estudios, desde estudios de campo en los trópicos, estudios funcionales y fundamentales sobre teoría de evolución. Si tienen preguntas durante el seminario del doctor Brooks, pueden hacerlo usando el chat que está a la derecha de su pantalla, yo creo que es por allá. Y al final de la charla vamos a pasar sus preguntas para que el doctor los pueda contestar. Por supuesto, pueden hacer sus preguntas en español si se sienten más cómodos y nosotros las vamos a traducir para él. Entonces, ahora voy a pasar al inglés. Hello, everyone. Welcome to the seminars of the Institute of Biology of UNAM that we are having every Tuesday at 11 during the time of the quarantine. So you can enjoy them by being safely in your house. So I'm Camille Triong, and today I have the pleasure to be with Daniel Brooks, who is the author of the book, The Stockholm Paradigm, Climate Change and Emerging Diseases, from the University of Chicago Press. So hello, Daniel. Very nice to have you here today.
Thank you very much. Very, very, very good to be here. Not great to be in Mexico City, but this is what we have today.
I know. Well, hopefully next time you can come to visit us. So Daniel Brooks is Professor Emeritus at the University of Toronto and Senior Research Fellow of the H.V. Mantle Laboratory of Parasitology from the University of Nebraska State Museum. He is a Fellow of the Royal Society of Canada from the Academy of Science and also of the Linnean Society of London. He has been awarded honorary doctorates from Stockholm University and the University of Nebraska and has been a visiting fellow of the Collegium Budapest, Stellenbosch Institute of Advanced Study, the Institute of Advanced Study of COSEC, and the Hungarian National Institute of Ecology. So Dan is an evolutionary biologist whose work ranges from field studies in tropical wildlands to foundational studies of evolutionary theory. His current focus is understanding the evolutionary relationship between global climate change and emerging diseases to develop proactive policy for coping with crises. So in 2019, as I told you, Dan and two colleagues published the Stockholm Paradigm, Climate Change and Emerging Disease, which consolidated more than 40 years of research into an understanding of the relationship between climate change and emerging disease, simultaneously giving us the bad news that the situation will get worse and that despite the threat, there is something we can do to mitigate the impact of those diseases. So I think this is a very appropriate talk with the situation that we're dealing today. And hopefully we're going to have a lot of public interested in this. So if you have questions during the seminars to Dan, you can do them using the chat that is on the right part of your screens here. And at the end of the seminar, we'll go through the questions so that Dan can answer them. So welcome again, Daniel. Thank you for being with us. I know you have been to Mexico several times before, right?
I have indeed. And I miss my friends and colleagues in Mexico.
Okay, but I'm sure they're all going to be here to listen to you today. So without further notice, I will let you start your talk.
Thank you very much. Thank you for the invitation. Thank you for the kind introduction. My presentation today is going to be very general. I won't speak very much about some of the technical issues behind this, because the most important thing in my mind at the moment is not so much figuring out the scientific technical points, but actually formulating proactive action plans for how we can cope with the problem that is facing us. I'm going to focus on emerging diseases today, but I want to begin by putting that in the context, a much larger context of global climate change. And I want to start with a statement that is going to sound a little strange, that global climate change unites humanity in a way that we have never been united before. Now, this sounds strange because, as you know, in many countries, including my native country of the United States, it seems that the issue of global climate change is a disunifying topic. So why would I say that climate change unites humanity in a way that it's never been united before? And I use the metaphor of what's called a black elephant. And the black elephant is a term that combines a philosophical notion of the black swan, which is something that is extremely rare and something you could not imagine until you actually saw it. And the elephant part of it is from the metaphor of the elephant in the room, which is an enormous problem that nobody wants to pay any attention to. So a black elephant is a highly improbable event that nobody wants to pay attention to, but we should have anticipated and we should be doing something about it. So now, why do I say that global climate change unites humanity? The reason for that is because global climate change is literally beyond belief. In other words, there are no nations that are favored, there are no social systems that are favored, no cultural systems, no economic systems, no political systems. There are not even any religious belief systems that are favored by climate change. Nobody is protected. Everybody is treated exactly the same way by climate change. So no matter what your particular beliefs are, this does not change the reality of climate change and the impact of climate change on our lives and the lives of subsequent generations of human beings. So now I'm going to focus just on the emerging infectious disease crisis, but most of what I say could be applied to other aspects of climate change: water, food, atmospheric warming, alternative energy, sea level rises. But I'm going to talk just about emerging infectious diseases today. So what are emerging infectious diseases? This is a much larger picture, a much larger phenomenon than most people understand, because emerging infectious diseases are pathogens of all kinds, from viruses to arthropods, that affect human beings and all of the non-human species that we rely on for our survival and for our socioeconomic development. It includes diseases that we have never seen before, as well as diseases that we thought we had either contained or eradicated and would not be bothered with in the future, that have come back to us. Most people know that there is an emerging disease problem, but they don't know how large that problem is. Now, what Eric Hoberg and Walter Bieger and I discovered in researching our book was that treatment and production losses, so the costs of treatment and the economic losses to production, either in terms of humans being out sick or losses of crops and losses of livestock from emerging diseases, conservatively are costing, and this is before this pandemic, before the COVID pandemic, it was costing the world more than the GDP of all but 14 countries on the planet, more than $1 trillion a year, approximately the annual GDP of Mexico. So if Mexico wanted to absorb the costs of emerging diseases for the entire world for 1 year, it would cost the entire annual budget of Mexico. One of the problems that we have is that the current approach by all health professionals is what is called do no harm. And this is a very conservative approach to medical treatment that actually has a very long history. But in terms of today, basically what that means is that health professionals will wait until there is a disease outbreak. They will then rush to deal with that outbreak. They will then tell everybody that there was no way we could have anticipated it. And once that crisis is finished, they will simply hope that there will be another one. And the crisis of emerging infectious diseases is that there always are more crises. This happens again and again and again, and it's happening more and more rapidly as the years go on. The other problem with the do no harm approach is that it's very good for photo ops. So here is a picture of some people carrying a dead body out of a village where there's been an Ebola outbreak. And this is very dramatic looking. It's very heroic looking. You have the people in space age suits. You have the doctor in the back who's looking upset. You have the people from the village behind wondering what's going on. And this looks very dramatic. It looks very heroic, but it does not work. This is not working for us. We are falling farther and farther behind in our efforts to try to cope with emerging diseases. So now I'm going to talk about 5 things that most people do not know about the emerging disease crisis that are important for us to understand. The first of these is that the emergence of disease does not require new genetic information, allowing a pathogen to move into a new host. Now, most people believe that an emerging disease occurs when a pathogen that is tightly co-adapted to one host somehow produces new genetic information that allows it to move into another host where it causes a disease. But it turns out that this is in fact not necessary. And rarely does the emergence of new genetic information occur before there is a colonization of a new host. In fact, it is the colonization of new hosts allowed by pre-existing capacities on the part of the pathogen that then set the stage for new emerging pathogenic capacities on the part of the pathogen to occur. And this is the basis of the Stockholm paradigm. Emerging diseases are expressions of pre-existing genetic capabilities in new ecological opportunities. So what happens is that no matter how tightly co-adapted a pathogen and a host may be in one particular part of the world, no matter how specialized that association is, there will be other hosts in other parts of the world that pathogen could infect if it had the opportunity. And when we are in a situation in which many new opportunities occur, this allows those pathogens to move into new hosts very quickly and in any part of the world where they happen to have the opportunity. We also have to understand that disease per se is not the evolutionary point of a pathogen. Pathogens are not species whose primary function in the world is to cause diseases in us and our domestic plants and our domestic crops and livestock. When a pathogen causes disease in a host, it means that host is actually marginally fit for the pathogen. It is a host where the pathogen can survive, but where the pathogen is not completely at home, is not completely comfortable. in those situations, the pathogen may not survive very well, but it may continue to reinfect that host. So that means that the host gets rid of the pathogen, but the pathogen keeps coming back because the opportunity for colonizing the new host has not been changed. The pathogen may be able to persist in the new host, but it may not be at home very well in the new host, and so it may continue to cause disease even after it has become established in the new host. Or the pathogen may in fact persist long enough in the new host to evolve ways that make the host fitness space not marginal anymore. In other words, it may, after it's been able to colonize a new host, it may or may not be able to evolve in ways that make the association between the new host and the pathogen less likely to be associated with disease. But we can't guarantee any of those things. The second thing we need to know is that there is a direct connection between climate change and emerging disease. Most people do not recognize that. There is a new large-scale FAO report that specifically says that they have found no connection between climate change and emerging diseases in crops and livestock, even though they do admit that they have found a direct connection between the outbreak of diseases in particular latitudes where warming is occurring as a result of climate change. So even in a situation where specialists are faced with the data, they still don't understand that there's a relationship between climate change and emerging disease, because until now, they haven't had an idea of how that connection might work. And this is something that we discovered. My colleague, Sal Augusta, who invented the term sloppy fitness space, Sal once said, the reason for this problem is that the answer was so obvious that we missed finding it, missed recognizing it for 100 years. And the answer is this: climate change, fundamentally, more than anything else, the effect of climate change on biodiversity is that climate change leads to movement. Whenever a part of the world begins to dry out, species that require moisture move away. Whenever an area becomes super wet, species that can't tolerate super moisture move away. So climate change catalyzes the movements of all kinds of species, pathogens, and hosts. And when this kind of mass movement begins to occur, then you have the situation in which both pathogens and hosts that have never seen each other before come into contact with each other. And so climate change sets the stage for a lot of mixing of pathogens and hosts and creates the opportunity for widespread emergence of disease. That means that emerging diseases are an evolutionary feature. They are not a glitch. They are not something that just began to happen in the last 20 years or 30 years or 50 years. This is something that has characterized evolutionary diversification for as long as there have been pathogens, hosts, and changing environments, which is essentially for the last 3 billion years. And this makes the planet, this is a metaphor that we sort of dreamed up about 15 years ago. This makes the planet what we call an evolutionary minefield of accidents waiting to happen. So you have all of these pathogens that could be moved around, all of these hosts that could be moved around as a result of climate change. And every time those movements occur, you will have disease emergence. Now, the third thing we need to know is that the evolution of human trade and travel amplified the background evolutionary mechanism of climate change catalyzing emerging diseases. The human trade and travel create massive new opportunities for emerging diseases. So if you have human trade and travel in the context of global climate change, then what you would expect is an enormous increase in the number of emerging diseases and in the places where those emerging diseases might occur. The relationship between human history, especially human history in the last 15,000 years, and climate change, say since the Holocene, is basically this. When conditions change, humans try to cope with the new conditions. If they cannot cope with the new conditions, they run away as much as they can. If they are not able to run away and find a place where the conditions are still suitable, they die. And this is a short, abrupt summary of what has happened to human beings in the face of climate change in the past 15,000 years or so. Now, the other thing that happened in the Holocene in those last 15,000 years is that is when human beings began to domesticate plants and animals and began to adopt more and more sedentary lifestyles. Now, at the beginning, when humans were not actually staying in one place, but they were domesticating plants and animals, when you had climate change events, then not only did the human beings move, but they took as many of the crops and the livestock with them as they could when climate change forced them to move. And what that meant was that they were bringing, in many cases, they were bringing new crops and new livestock as well as themselves into new areas where everything came into contact with new pathogens in the new areas. And in some cases, old pathogens were brought with them and introduced to the new areas. And so suddenly you have this big explosion. And at that point, it begins to become apparent that just running away is not actually necessarily making the situation better. So the next thing the human beings did was that they began to settle in particular places and not run away when there was a climate change event. They attempted to deal with the problem more and more and more without movement. And this leads us to the fourth point that we ought to understand today, and that is that cities are a problem, not a solution when it comes to climate change and emerging diseases. Sedentism, that is settling in one place for a growing season and then for an entire year, which then ultimately led to urbanization. Those things, those changes in human behavior changed our evolutionary trajectory. They changed what human beings had been doing for thousands of years to survive. And they took away our traditional or our ancestral evolutionary research escape route, which was to run away from trouble. Now, once we're locked into cities, we have to stay in place and deal with the problem no matter what. Urbanized civilizations before the last 250 years, that is before the Anthropocene, before the Industrial Revolution, have experienced climate change, many of them. And oftentimes you will hear people say, well, human beings have been faced with climate change before, and we've always survived that, so we're going to survive this. But that, in fact, is not true. Every time a human civilization before the Anthropocene was affected by severe climate change events, even short-lived ones, that civilization was destroyed forever. Ultimately, it fell apart, people left, and nobody ever came back. And that's because cities limit our ability to run away from danger. So by the time we have to leave, it's too late to save the city. This is a sunrise photograph of Angkor Wat in Cambodia. This was a wonderful, enormous, modern civilization that was done in by fairly moderate episodes of climate change. Fluctuations in flood and drought, ultimately broke their wonderful water system that they hadn't taken care of. And eventually, after just a couple of generations, they said, we can't cope with this, we're leaving. And this is typical of what has happened to pre-Anthropocene cities. Cities today are population density and connectivity traps that increase the risk of disease. They are warm. Our cities today, our large cities today, are typically 2 to 3 degrees Celsius warmer than the surroundings. They require a constant flow of energy, water, and material goods in and out, which means that they are connected with the rest of the world and whatever pathogens the rest of the world may be bringing in. They have high population densities, lots of people with low kinship ties, which means that you don't know, typically in cities, you don't know that many people. That means that it's more difficult to understand who to trust and who to cooperate with. Cities have extreme division of labor. They're very, very specialized with the extreme interdependency that brings to it, which means that if you have a breakdown in one part of a chain of interdependency, the whole infrastructure is brought to a standstill. Anthropocene cities are safe environments for many zoonotic diseases. Our urban green spaces that we feel are really important for purifying the air and for giving people nice places to live and hang out are also environments where a large number of zoonotic diseases and their disease reservoirs exist and survive. And finally, and more importantly, and we see this with COVID in particular, the high level of standard of living that characterizes a lot of people in big cities and characterizes the reason why many people are attracted to big cities. That lifestyle is always supported by an underclass of human beings that are undernourished, undereducated, underserviced by the health industry, oftentimes undocumented. And those are the people who wash our clothes and clean our homes and do our laundry and prepare our food and clean the bedpans and the sheets in the hospitals. These people are everywhere. They are invisible and they are treated poorly by us. And as a consequence, they are the people who are most likely to become sick when a new pathogen emerges within a city. And because they're poor, they are not able to stay home while they're sick. So they are the people who not only will become sick first, they're the people who will continue going to work while they are sick. In 1950, 30% of human beings lived in cities. By 2050, just 100 years later, and just 30 years from now, we estimate that 70%, probably even a higher percentage than that, of human beings will live in cities. So this is an enormous problem. If cities are a major danger point for infectious diseases, we are in fact making things worse rather than making things better for ourselves. And finally, most people do not understand that we can be proactive about coping with emerging diseases. Most people believe, as most health professionals believe, that we cannot predict any of these outbreaks. We cannot do anything about it until they happen. And then once they happen, then we have to try to cope with the problem. This, in fact, is not true. And that is the major contribution, the major insight from the Stockholm paradigm, is that, in fact, there is a way to be proactive about emerging diseases. Okay, so if it turns out that colonization of a new host only requires new ecological opportunities for exposure based on specific pre-existing capacities that the pathogen already had, those pre-existing capacities are predictable. And that means that if we can anticipate where a disease is likely to be transported geographically, we can anticipate how it will move into new hosts in the new places and how it will be transmitted and how it will behave. So we can, in fact, anticipate a lot about these emerging diseases. At the same time, we understand that this pattern of disease emergence is just going to be accelerating for at least the next 30 years. Now, this leads us to what we call the strategic metaphor, or anticipate to mitigate. We cannot eliminate these emerging diseases, but we can mitigate their impact. We can reduce the effect that they have. We can reduce their costs on us. If we know what is coming, we can buy time while searching for long-term solutions. That means if we know what's coming, we can try to mitigate, we can try to limit their impact. And that helps us, that helps researchers with vaccines and medications and so on. That gives them more time to try to come up with real long-term lasting therapeutic treatment regimes. The tactical metaphor, in other words, what do we do, is what we call the Dhamma Protocol, or finding them before they find us. That's what we have to do. And the Dhamma Protocol is an acronym that stands for document, assess, monitor, and act. And this is a protocol that stems directly from the activities of people who have been involved in major general biodiversity inventory projects, people interested in biodiversity and sustainable socioeconomic development in tropical wildlands, for example. This is just adapted directly to the issue of emerging diseases. The fundamental services that Dhamma projects give us is an understanding of what pathogens are already living with us, but have not caused diseases yet. So, for example, in 2005, 2 different laboratories in China published papers recognizing that there were SARS-like viruses living in bats in Wuhan, China, and warning that they could, in fact, be a problem under certain circumstances. If that advice, if that information had been acted upon, exposure could have been reduced. And if exposure was not reduced to 0, we would have been better able to understand the emergence when it first began to happen. The Dhamma Protocol, Dhamma projects also give us some idea about what pathogens currently do not occur in our home countries and our home cities, but might very well be coming. That would give us, knowing what is coming, gives us the opportunity, knowing what is coming and knowing how it will behave when it arrives, that will allow us to help change the conditions to make it more difficult for the disease to establish. Things like if we anticipate that malaria is moving into a particular area, before it arrives, we know to begin mitigating mosquitoes. We need to understand how to do that. We also need to understand that if certain diseases are coming, they're not here yet, but we expect them to arrive at some point, the Dhamma projects can give us some idea of what the earliest warning signs are. What would be the first sign that this fungus has shown up in our crops, that this virus has shown up in our cattle, that this worm is showing up in our children? What are the early warning signs to help us, again, to help us mitigate the impact of the disease? The Dhamma Protocol is also occurring at a time when the crisis is so great that we really don't have a lot of time. We need, not only do we need to be doing these kinds of proactive activities, but we need to do them in very focused ways, in very efficient ways. We can't simply go out and survey the entire planet for every possible pathogen everywhere and then decide what to do. We need to use the knowledge that we have already about diseases and emerging diseases and their relatives to look specifically in the habitat interfaces between wildlands and managed habitat, forests and agricultural lands, forest edges and suburbs, suburbs and cities, cities and their green spaces. We need to look in specifically in those interfaces because those are the places where you have one host that is the reservoir, the primary reservoir for the disease, carries the disease, is not sick, but it transmits the disease to crops or livestock or human beings across the habitat interface and causes the disease problem. So we also need to look in those interfaces specifically to identify the reservoir hosts. In the case of COVID-19, for example, we already missed that opportunity. We did not act on the information that the virus was occurring in the wildlands and could be transmitted into the food supply and into urban settings. Once that happened, once the disease emerged as a pandemic of human beings, we then did not act on the realization that if it could go from the wildlands to food animals to human beings, it could go in the reverse direction as well. And so we missed the opportunity worldwide to begin monitoring non-human hosts for the possibility that they would become new reservoir hosts in new countries. So there was some research done in Hong Kong where a laboratory found that cats and dogs and ferrets, among companion animals, were all susceptible hosts for COVID. And every evolutionary biologist immediately said, well, if it's cats, dogs, and ferrets, that means that basically you're saying all carnivores are potential reservoir hosts. So not just domestic animals, not just domestic dogs, not just domestic cats, not just domestic ferrets, but all of their wild relatives as well. And we did not act on that. And so one of the first reports we had was in the Netherlands a few months ago, where some minks in a mink farm were discovered to be infected with COVID. They had been infected by one of the workers, and then later they infected another worker or other workers in that mink farm. And today there's a report in the Washington Post in the US that the same thing has happened at a mink farm in Utah. We should have understood this. We should have known about it. We should have been better prepared for it. We need to understand that we can be better prepared for this. We don't have to, as Eric Hoberg says, we don't have to be continually unpleasantly surprised when something new and awful happens to us. We don't have to continue to allow these emerging diseases to victimize us to the extent that they are. One of the things that's really important to do in the context of any Dhamma project is that we have to harness the people who are going to be most affected in the next 30 years by things like the emerging disease crisis. We have to get the energy and the strength and the determination of our youth. We have to let them know that there are things they can do that are positive, that are hopeful, and then we have to let them do that. And this is what's being called, some people are calling this the let the young people drive the car or the truck or whatever concept. The Dhamma Protocol has to be foremost in our total global strategy for dealing with emerging diseases. It can't be something that we just add on as a peripheral sort of item. Because once a pathogen becomes established in a new host, as a result of the Stockholm dynamic, as a result of predictable pre-existing capacities, once the pathogen becomes established in a new host, that is the point at which novel evolutionary capacities may emerge, and they are not predictable. So the only time we have to when we can make good predictions about disease emergence is at the point at which the emergence may happen. If we wait until the emergence has happened and new capacities, new pathogenic capacities begin to emerge that are not predictable, then our only option is this unsustainably expensive crisis response that we're engaged in now. So Dhamma has to be at the forefront. It has to be at the beginning, not at the side, of our global strategies for dealing with emerging diseases. We cannot afford business as usual. We have to understand that the global meltdown caused by SARS-CoV-2 was a baby pandemic. The 1918-1919 Spanish influenza pandemic killed 10% of the world's population of humans. That would be the equivalent of 750 million dead people in the world today, as opposed to 750,000 dead people in the world today. So we are nowhere near the catastrophic impact in terms of death of the Spanish influenza, and yet the global economy has melted down. So this tells us that our highly globalized economy is actually not very robust in the face of things like emerging diseases, even if those emerging diseases are not nearly as catastrophic as some previous pandemics that we've had. So this meltdown that we're seeing as a result of the current pandemic shows us the cost to the world of not adopting Dhamma protocols for anticipating and coping with the emerging disease problem in a proactive way. And we don't have any more time. 5 years ago, 10 years ago, people like me were saying, we don't have much time, we don't have much time, we don't have time. And we were wrong, we were too optimistic. The Canadian science fiction writer Peter Watts once recently said in a talk I heard him give, he said, history tells us that the optimists are always wrong and the pessimists are always too optimistic. And this quote from another science fiction writer, from Isaac Asimov, from 70 years ago, is an example of that. It turned out we didn't have much time after all. Oh, we thought we had more time. Well, we didn't, and we didn't do anything with the little time we had. And so now, what do? We are at that point with respect to not just emerging diseases, but every other threat multiplier component of climate change. And we have to buy time to survive. That is the value of hope for the future, is that we can do proactive things to buy some time to save ourselves. And our job right now, whether it is, in my case, working with emerging diseases, but anybody else working with climate change threat multipliers, our job now is to try to save as much as we can. And understanding that everything we do from this day forward will be some form of triage. We cannot reverse this. We cannot stop it. We can only try to cope with what's coming at us and mitigate its impact on us and future generations. Thank you very much.
Okay. Thank you very much, Dan, for this very interesting and very actual topic. So if you have questions, please, you can do them using the chat on the right part of your screen. So I will start with one question. I was wondering, you talk a lot about the ability that we have to do prediction, and that we have to do prediction before the disease is really here. So I was wondering if you could tell us a little bit more about how do you actually do these predictions? What kind of data do you use? And yeah, how do you do this?
Well, interestingly enough, the major part of the first step in predicting what's going to happen, of course, is to know what you have. You know, if you haven't documented the world's biodiversity, you have no idea of what's there, what the options are. So this all begins with doing the kinds of intensive, rapid inventory projects that biodiversity specialists have been arguing for 35, 45 years. We have to do that for pathogens. The second step is very interesting, because that's a connection between a very practical matter, which is how do we develop policies for coping with diseases, and some very basic evolutionary biology, because this is what we call the phylogenetic triage. If you do an inventory of, say, microbes, you're going to find an enormous number of microbes, most of which are not going to have anything to do with disease. So how do you rapidly go through and sort them out? And the easiest way to do that is to say, here's what we're looking for. We're looking for the evolutionary signatures of microbes that are already known to cause disease, or other microbes that are very closely related evolutionarily to microbes that cause disease.
Mm-hmm.
So for example, if I say to you malaria, and I say that to anybody watching this, I will guarantee you that almost everybody, if I say malaria, the first thing that will pop into their mind is mosquito.
Yes.
Not the actual parasite in the blood cells.
I agree.
Now, what does that mean? It means that no matter what species of malaria we're talking about, no matter what part of the world it originates in, if it comes to your area, you can anticipate that it's going to be transmitted by mosquitoes. So the first thing you do is you begin to look at all the different mosquitoes in your area and find out which ones could be suitable reservoirs for an introduced malaria species. And the first thing you do is you say, all right, let me look at the phylogeny of mosquitoes. And I go, okay, now over here is a whole bunch of mosquitoes that do not feed on mammals. Okay, we don't have to worry about them. They're not going to give us malaria. Then there are some more that feed on mammals, but they only feed one time on mammals. So we don't have to worry about them, because mosquitoes in which the females only feed one time on a mammal, they can't transmit the disease. So now we're down to a small group of mosquitoes that feed on mammals, and in which the female has to feed twice, once to nourish the unfertilized eggs, and again to nourish the fertilized eggs for them to be laid. So now you say, in that group, that's relatively small group of mosquitoes with that kind of evolutionary behavior, which ones are in my area? So now you know the potential vectors of disease. You know that there's the possibility of malaria possibly coming to your area. For example, malaria historically, within the last 300 years, 400 years, has been in the northern part of North America, north of Mexico. It's been in the United States. It's been even as far north as Ontario, Canada. So we know it could come back with the appropriate environmental conditions. So here's a disease that could potentially be coming to us. We should know all of the mosquitoes that are in the United States and Canada that could potentially be vectors, and we should be checking them. And we should have plans for coping with that. So knowing this now we seem that we're a long way away from phylogenetic analysis and very technical evolutionary biology, but now it becomes very practical, because you say, there's a threat. Now let's do some more evolution and natural history of mosquitoes. So almost everybody knows that female mosquitoes are the ones that feed on blood. Mm-hmm. So the question is, what do male mosquitoes do besides fertilize the females? Okay, what do they eat? Well, it turns out that male mosquitoes generally feed on plants. So they suck the juices from plants. And of course, it turns out that they have different species of male mosquitoes. The males of particular species of mosquitoes have preferences. So once you know what the plants are that they prefer, number one, don't plant any of those plants in your garden. Number two, because if you have plants that attract male mosquitoes in your garden, and then you have a water bath for the birds to come into your garden, and you don't check the water in the water bath for mosquito larvae, then you have created a mosquito factory. The males are there feeding on the plants, the females come where the mosquitoes are, and the females lay the eggs in the water bath. So all you do is you tell people, don't plant these kinds of plants in your garden. If you have a water bath, make sure that you change the water every 2 or 3 days. If you see any mosquito larvae, pull it out, throw it out. And this is taking advantage. This is a very practical way to take advantage of some very esoteric technical information about evolutionary relationships. So we go all the way from the evolutionary history of mosquitoes down to what do you do in your backyard to keep your children from getting malaria?
Yes. Yeah, well, that's a good point. And it also tells us that it's really important to know natural history of all these organisms.
Natural history and evolution is really important.
Yes.
It's very important. And,
Yes.
and of course, this is one of the tragedies of the situation we're in right now, is that the number of natural history people, the number of field biologists who are being trained is diminishing rapidly. The number of them who are finding jobs is diminishing rapidly. The amount of money for research that's allocated for people like that is going away. Support for natural history collections, which are our only information about how things used to be compared to how they are now. That's our only database for that. Natural history collections are disappearing rapidly. They are being, for example, the most terrible example is of neglect is the natural history collection, the National Natural History Collection in Brazil that actually burned down last year with the loss of enormous amounts of information and specimens that can't be replaced. And so, yes, exactly. We are in a situation where the funding agencies are digging in the wrong place, in a sense.
Yeah.
The money is not being allocated in the most effective way. So if you do not try to mitigate the emergence of disease, then you can't possibly put enough more and more and more money into producing vaccines. Because as we've seen, no matter what everybody says, we'll have a vaccine next year. So here's a question for everyone to think about. All of the people who are working on the COVID-19 vaccine right now, what were they doing 1 year ago?
Yes.
Okay. Were they working on the Ebola vaccine that we don't have, the HIV vaccine that we don't have, the Zika vaccine that we don't have, the Hanta vaccine that we don't have, and so on and so on? We found one of the most unhappy things that we found in our research for the book was that, in fact, the 20-year period in human history that was most productive for producing vaccines was 1880 to 1900. The number of new vaccines produced every year has been decreasing ever since 1900. So we're losing that battle. We cannot vaccinate our way out of the problem unless we can mitigate the impact of diseases enough to give the vaccine producers more time to actually succeed. And we can't constantly take people who are working on one vaccine and say, oh, I'm sorry, you can't work on that vaccine anymore. Here's this other vaccine now. The government will not give us money for the Ebola vaccine now because they're giving money for a COVID vaccine. And so the poor vaccine workers are all over the place. They don't have enough time to do their work properly. And the way for them to be able to do their work properly is to provide a lot more money for natural history collections, for taxonomists, for field biologists, for phylogeneticists, and so on.
Yeah, about vaccination, we have a question from Francisco Vega Silva, who would like to know what is the role of vaccination programs and other biomedical interventions in the zoonotic disease-related complex causal eco-evo bioculture chains that you suggested in your theoretical framework.
Well, the necessity for a vaccine is an indication that we have failed to mitigate the emergence of a disease. So once we need vaccines, it means that we have allowed in this case, a zoonosis, but other pathogens as well, to become established within human society, so that it is now our problem. It's not a problem that we can cut off at its source, because we now have become our source. So once this is established, then of course, medicating people who are sick and vaccinating people who are at risk becomes the only way we can cope with a disease once we have made it become a problem for us. So, and this is a really important question, because some people will sometimes say to me, well, we only have a certain amount of money for disease research. What money should we take away from medication programs and vaccination programs to fund your DAMA program? And I say, no, I disagree with this completely. We should not take any money away from vaccination programs. Those programs, in fact, are underfunded and need more. The same thing with medication. We need new money. The reality is that if we are going to survive what is coming at us at an accelerating rate right now, it's going to take more money. It's going to cost money. We're going to need to do more vaccination. We're going to need to do more antibiotic and other things. There are a whole bunch of things that are ideas that are being done currently, especially in agriculture. But we have to understand that we have solved all of the easy problems when it comes to medicating and vaccinating. We should have known, for example, if anybody had asked a veterinarian, we should have known that it was highly unlikely we would produce a COVID vaccine quickly, because there are coronaviruses that cause a lot of problems in veterinary, especially beef production around the world. And the veterinary scientists have not yet been able to produce a suitable, effective coronavirus vaccine for them. Coronaviruses just are a problem. The viruses that are amenable to vaccine production, we've got them. The bacteria that can be handled by antibiotics, we've done that. But in producing antibiotics and distributing antibiotics widely, of course, we have engaged in global experiments in natural selection, with the predictable result that we have created antibiotic resistance,
Yes.
which then fuels the need for yet new antibiotics, which makes the cost go up.
Yes, so coming now to our economy, we have a question from Hugo Harlan Merija from Madrid, who would like to know, do green economies can be a solution? I heard in one of your talk in Hungary that alternative energy sources for humans are not necessarily a real solution.
Hugo, ¿qué tal, amigo? Hugo is one of, in fact, is one of our colleagues in this larger Stockholm paradigm group of cooperating biologists. And this also is an extremely important question. And there's not a single answer. So, for example, if making green spaces in cities is part of a green economy, we have to understand that the benefits of having green spaces in the cities are also accompanied by costs of providing suitable habitat for pathogens and reservoirs of pathogens. So there are of course a lot of things we can do that involve so-called green economies, and things like circularizing local economies, revitalizing rural areas. In the biomedical area, there's a really interesting concept called the economics of well-being, as opposed to the economics of profit. And these are all ideas that all potentially are going to be helpful. But we have to understand that there's not going to be one solution that's going to solve everything. And no solution is going to be 100% benefit with no costs. Because climate change is a biological problem. It was, created by a biological system primarily. It affects biological systems enormously. And that means that anything we do is in an evolutionary context. And as a consequence, we have to understand that whatever we do to help in one area may have unanticipated negative consequences in another. And we have to balance those kinds of things out.
Mm-hmm. Yeah, so talking about climate change, we have a question from Victor Sanchez Cordejo, who would like to know, in addition to climate change, a little bit like to follow on what you just said, that deforestation can exacerbate emerging diseases to make a perfect storm.
This is interesting. This is a topic that has come up in the last few months. The notion that deforestation somehow drives pathogens out of the forest into human beings. But the reality is that what the relationship between deforestation and emerging diseases is that the process of deforestation creates additional interfaces between human beings and the wildlands. So it's not destroying the forest per se, it's the fact that the process of destroying the forest brings more and more human beings into contact with the forest margins. Because you have to understand that all zoonotic diseases survive particularly well in wildlands that have not been heavily deforested.
Mm-hmm.
So if you have wildlands that are not affected by deforestation, but human beings still live on the edges of them, you're going to have a lot of emerging diseases. On the other hand, if you have deforested areas, which then human beings move away from, so that you allow the deforestation to diminish, moving human beings away from those edges will decrease the impact of diseases. So the important thing here is that it's not deforestation per se that creates disease emergence. Deforestation creates the opportunity for human beings to come into contact with the pathogens that live very happily in the wildlands.
Yeah, that's to follow on this. Victor Sanchez Cordejo also said, what do you think on this, the biodiversity dilution effect to decrease the probability of pathogen jumping into humans?
Yeah, this is unfortunately, this is a wonderful mythology that would be great if it were true, but it's not true. The reality is that the dynamic that we know, the Stockholm dynamic of pathogens moving into hosts that are not their original hosts, simply as a result of species moving about, that means that there's an increased likelihood that even if your original host goes extinct as a result of climate change, the pathogen will survive in a different host. And we have a lot of evidence of this. In fact, Eric, this was one of the first insights that Eric Hoberg had back in the late 1980s, when he discovered that some groups of tapeworms that live in alcid birds in the Arctic are actually 30 million years older than the bird groups that they infect. So those pathogens, those tapeworms, in fact, not only were they living in something else before the alcids evolved, but the parasites themselves survived the Cretaceous, the Alvarez asteroid impact, the KT boundary mass extinction. They killed almost all of the original hosts, but many of those pathogens survived. And so it turns out that we cannot, in a sense, extinct our way out of the problem. We cannot hope that as more and more hosts go extinct, they will take disproportionately more and more pathogens with them. It's the opposite. The evolutionary record is that it's actually the opposite sort of dynamic.
Mm-hmm, mm-hmm. Next question comes from Carmen Villalobos, who'd like to know what are the advantages of applying the DAMA protocol within multidisciplinary groups researching emerging diseases.
It would be wonderful. We would love to have that happen. In the chapter on the Dhamma Protocol in our book, we actually talk about how there are a number of international programs that tend to be mostly what we call top-down. So these are international programs organized at a very high level, and sort of university-based and sort of filter their way down. Whereas the Dhamma Protocol is very bottom-up. It's based on working with local people, citizen scientists, muddy boots on the ground kind of thing, moving up. But at some point in the middle, all of these top-down programs and these bottom-up programs need to come together and communicate with each other. So the fundamental, the answer is this would be enormously advantageous. This is exactly what we need to do. And the more of this kind of cooperation we can find, the better. Once again, this is an extremely important question, and it has an easy answer in principle. But when it comes to saying, okay, who's going to provide the money for bringing a Dhamma protocol into our existing research program? Because our existing research program, we just barely have enough money to do what we do. We can't take 20% of our budget and give it to somebody new who's coming in. So the real problem with cooperation is, once again, it's a question of financing it. Mm-hmm. So we know what to do. We know how to connect. We know how to cooperate. The scientific, this kind of platform for internationally producing scientific presentations and seminars, even when everybody's locked down and nobody's traveling, this is an example of how well the scientific community cooperates. Mm-hmm. We know how to do this if we have the ability to.
Yes. So to follow on this, we have a question from Naomi Chavez Castañeda, who'd like to know, according to your experience, so how should we act in favor of research on emerging diseases? Well, one solution would be to cooperate more, but you have other ideas.
All of the current large-scale surveillance and monitoring programs need to be front-end loaded with a Dhamma protocol component. In other words, they need to broaden what they're doing. We need much more cooperation and conversation between basic evolutionary biologists and medical and veterinary and agricultural health researchers. Eric Hoberg, who I keep mentioning, one of my 3 authors on the book. Eric worked with U.S. Department of Agriculture for more than 25 years and could never convince them to add anything about climate change and emerging disease and the possibility of diseases emerging in livestock or crops anywhere as a result of climate change. So it was constantly, no, Monsanto will come up with an engineered version. We've got drugs, we've got fertilizers, we've got chemicals. It's not a problem. And from the agricultural standpoint, the basic assumption is, well, if it does cost us more money because we're losing production due to disease, we will just increase the prices of the food and pass it on to the consumers. So what we've discovered is that in the area of climate change and disease and food, nobody cares about emerging diseases. This is just considered to be the cost of doing business, and we pass the cost on to the consumers. So in the United States, for example, meat prices have increased by 40% in the last 6 months. Mm-hmm. And that's not even directly due to a disease in the food. But we have to understand, for example, that one of the reasons we have the COVID outbreak is because of the African swine fever outbreak in China 6 months before the COVID outbreak in China. African swine fever in the spring, in April, May of 2019, destroyed 50% of China's pork production. And this was at exactly the same time the United States and China were having a pissing match about trade and all this stuff, and nobody was cooperating, nobody was talking. So there was a pork shortage within China, which drove many people into alternative animal protein markets, which increased the demand for people to bring animals out of the forest into the markets. And in that particular culture, in those particular places, what you had were live animals being kept in the markets. And someone would then say, I want that particular bird, or I want that particular animal. And then that animal would be butchered and sent home, or they would take the animal home alive and kill it and eat it later. So last November, when some friends of mine who are young virologists in Hungary, when we first began to realize that something was happening in China that looked like SARS, I remember one of these young guys said, I was looking at some of the satellite photos of those markets in China, and the first thing that came into my mind is that these are SARS factories. These are exactly the places where you have pathogens and hosts getting mixed together. So it's a little microcosm of what climate change has always done evolutionarily. But now you mix them together, things get all mixed around. And so you then have this coronavirus getting from bats into, say, dogs or cats, which then allow new variants to survive, which then can get into human beings. And so what we need to do is we need more real cooperation between health professionals and evolutionary biologists. We have to stop believing that this is fundamentally a problem of vaccines and medication. Mm-hmm. Vaccines and medications are things that we need to cope with a crisis after we have failed to keep the crisis from happening. And we're losing so much money, we can't keep doing that. So we have to go to the other end of it. We have to go to the point, the source point.
Mm-hmm. Yes. And so Edmundo Gonzalez Santillán has a good point saying the main problem, knowing all this medical eco-information, how do we pass on to our governments?
Well, people like me have to keep talking and talking and talking and talking. and hopefully at some point somebody will pay attention. Now we had today is Tuesday, so Sunday morning, I found a preprint on ResearchGate, just going through my ResearchGate. I found a preprint of a large review article that is in press in the journal called Cell. And it's a review article about how the whole COVID emergence happened. And they actually cite as their reason, they say it is this stepping stone from the bats to the markets to humans, this stepping stone dynamic, and that the mathematical model for that stepping stone dynamic was published in 2015 by the one of our cooperating groups, the one that Walter Bieger, our other co-author, is part of in Brazil, in Curitiba, Brazil. That was published in 2015, the mathematical model that showed how feasible that was. And in the preprint for this article that's about to appear in Cell, they cite that model and say this is the evolutionary justification for what we're saying about how COVID got out. And the important thing about this is that there are two authors on that article, and the second author is named Fauci.
Okay.
So this is the first time we have any indication that somebody at a high level, a high policy level in a government is paying attention to this, to these ideas and to this notion that we need to try to get ahead of the curve. We can't just wait for the crisis to happen.
Mm-hmm. Yeah, unfortunately, it's a little late to do it, but it's better late than never.
Well, it's okay. It's too late for this particular pathogen, but as people like Fauci and all of the other, you know, high-level public health people know, and hopefully the agricultural people are beginning to understand, this particular pathogen is not the worst thing that could happen. It's not the worst thing that is going to happen to us. African swine fever is still causing enormous problems. It has caused pork prices in Hungary to double in the last year. There is a rust fungus that is killing wheat in the Middle East and has now moved into Southern Europe that does not respond to any known fungicide, and none of Monsanto's rust-resistant GMO strains of wheat are resistant to this rust strain.
Mm-hmm.
If we lose wheat as a crop, that's almost 25% of the calories that human beings eat every day on this planet.
Mm-hmm. So finally, we have a question from Omar Lagunas, who would say, so I'm going to say it in Spanish and then in English again. Según su experiencia, ¿qué tan posible es que en próximos años experimentemos extinción de parásitos nativos debido a la introducción de especies exóticas? So Omar would like to know, according to your experience, how plausible it would be in the next few years to have the extinction of native parasites due to the introduction of exotic species.
Yeah, well, this is also something that would be really wonderful if it were true, and it turns out not to be the case. We now have a growing number of cases in which introduced host species are acquiring native parasites. In some cases, they are bringing introduced species of parasites in which native hosts are acquiring. And in some cases, we have exotic species being introduced that do not bring their native parasites in with them. But that seems to be just founder effect. You know, if you bring in a very small number of these hosts, it's not likely that they're going to be bringing in a lot of their parasites with them. But we have a source of information about this that people tend not to pay too much attention to. And that is, if you ask almost any parasitologist who works in a zoo, Parque Zoológico, they will tell you that there are a lot of pathogens get passed around within the zoo among the different exotic animals and between exotic animals and native species. So it seems that yes, we should be looking for this possibility, but it seems very clear that every place on this planet is at risk for the introduction of exotic pathogens, and every exotic host that's introduced is at risk for acquiring local pathogens where it shows up.
Mm-hmm. Yeah.
So once again, we can't. I mean, as I said, the human history is that whenever there's a problem, we run away from it, traditionally. but that has not worked. Because in general, when we have run away from one problem, we have taken some pathogens with us, and then we have found new pathogens where we show up. And that's why some paleoparasitologists suggest that the earliest human beings that still lived in the forests and forest edges may have had only 15 or 20 different pathogens. And today, human beings globally host at least 1,500 different pathogens. So our idea of running away from one problem has not helped us.
Yeah, exactly. Well, thank you very much, Daniel, for this interesting talk. And I remind everyone that next Tuesday, we'll have the seminar by Alejandro Tomescu from Humboldt State University about the steel concept, an Evo-Devo perspective. So, muchas gracias, Daniel, para su charla muy interesante. Y la próxima semana vamos a tener al doctor Alejandro Tomescu de la Universidad de Humboldt State en California del Norte, que nos hablará sobre The Still Concept, an Evo-Devo Perspective. Bye.
Fue mío. Hasta la próxima vez.
Thank you. I hope it will be in Mexico City.
Ojalá. Chao, chao.